Hey guys, so today we are going to discuss about the question called as number of increasing paths in a grid. So this is a Leetcode hard question. So there is a similar question as well. So that's called as longest increasing path in a grid. So these two are a bit similar, but I would say this is a bit complex than that one. So I would recommend you to solve that question before getting into this question. So let's start reading the question. So you are given an m into n integer matrix called as grid, where you can move from a cell to an adjacent cell in four directions. So these four directions would be up, down, left, and right. So return the number of strictly increasing paths in the grid such that you can start from any cell and end at any cell. Since the answer may be very large, return its modulo 10 power 9 plus 7. So what they're trying to say is they'll be giving you a matrix or a grid which contains some integers. So it contains m into n integers. So what you have to do is you have to find the number of increasing paths in that grid. For example, let's say we have this grid. We have a grid. So let's take a grid. Let's take this example. So let's take we have a grid called as this, which is, let's name it as something called as grid. So this contains numbers like 1 1 7 3 6 2 4 5 8, right? So let's know what are increasing paths here first of all. So increasing path is nothing but a path which would be a strictly increasing order. So for example, let's say if we start from this one, so the increasing path, for example, one of the increasing path would be 1 2 3, because 3 is greater than 1, right? So this will be strictly increasing path. So this is an increasing path. So what they are asking is you have to find in the entire grid how many number of increasing paths are there. So that's the requirement. So how do we find the number of increasing paths first of all? So let's take a normal brute force approach. So for example, let's start from the beginning, from this one. So from if we start from this one, how many number of increasing paths are there? For example, let's take from here, you go to the adjacent one. This is not increasing. You come back again, you go to the another adjacent cell, which is 3. So this is increasing, right? So this is one increasing path. And one more thing, which is a single number is also increasing path. For example, let's say this 7 doesn't have any other adjacent cell which is greater than 7, right? But that doesn't mean that it doesn't have an increasing path. So even a single number is also an increasing path. So starting from 1, so 1 would be one increasing path. So as we have seen, one is not, the adjacent one is not increasing greater than 1. We come back, we have come to 3, right? So 3 is greater than 1. So this is one increasing path. So this would be one increasing path from 1. So now let's see the adjacent cells from 3. So 6 is greater than 3, right? So this is one increasing path. 1 3 6. So coming to 6, let's see the adjacent cells from 6. So 1 is not greater than 6, come back. So next one is 2 is not greater than 6, come back. Next one is 5 is not greater than 6, come back. So that actually means there are no adjacent cells from 6 which are greater than 6. So again, coming back from 6. So now coming back to 3, we come back to 3. Now we go to 4. So now 4 is greater than 3, right? So this is one increasing path. So 1 3 and 4, this is one increasing path. So from 4, let's see the adjacent cells. So 5 is greater than 4, right? So this is one increasing path. So the other increasing path would be 1 3 4 and 5. So now starting from 5, let's see the adjacent cells of 5. 1 is 6. So 6 is greater than 5, right? So this would be one increasing path. 1 3 4 5 and 6. So now 6, from 6, let's see the adjacent cells. So 1 doesn't have it, 1 is not greater than 6, coming back. Let's go to 2 is not greater than 6, so coming back. So 6 doesn't have any more cells which are greater than 6, so coming back from 6 to 5. So the next adjacent cell to 5 would be 8, right? So as 8 is greater than 5, so this would be included in the path. So the new path would be 1 3 4 5 and 8. So this would be the new path. So now starting from 8, let's see the adjacent cells if there are greater than 8 or not. So one of the adjacent cell would be 2 is not greater than 8, right? So coming back from 2, so there are no adjacent cells from 8, because one would be out of the boundary and another would be out of the boundary and another would be 5 which you have come from. We cannot include that 5. even though it's not greater than 8. So from 8 there are no more adjacent cells, right? So that actually means from 1, these there are, if we start from 1, so these are the number of increasing paths: 1, 2, 3, 4, 5, 6 and 7. So from 1, these are the increasing paths, so which would be 1, 1, 3, 1, 3, 6 and 1, 3, 4, 1, 3, 4, 5, 1, 3, 4, 5, 6, 1, 3, 4, 5, 8. So these are the increasing paths. So similarly we find number of increasing paths from this one, number of increasing paths from this 7, and similarly from the rest of the cells. So this would be the brute force approach. So all you have to do is you have to perform backtracking from each and every cell in the matrix. So this would be a brute force approach. But how do you optimize this solution? Like how do you optimize the solution? So based on this approach, don't you think we are doing the same repeating process again and again? For example, when you have come to 3, this cell, this 3 cell, you have gone to 6, right? So you have found the number of you have gone to 6 and you have found the number of increasing paths from 6. Like you have checked whether there are any increasing paths from 6 and you have come back, right? So and you went to 4 and you have come to 5 and you went to 6 again. So you're again doing the same thing again, right? From 3 you have done the same thing, and from 5 you're doing the same thing. So what you can do is you can store the number of increasing paths from a particular cell at some place. For example, you have a place somewhere else and you have stored the number of increasing paths from 6, and when you have come to the 6 again from 5, what you can do is instead of doing the same repetition process again, you can just take the value from here and you can just return this value to 5 and let 5 know the number of increasing paths from 6 would be 1. So that's how like you can optimize this. Like, and we might get a doubt, how does this help? Like how can we know, like if 6 has number of increasing paths would be 1, then how can we know the number of increasing paths from 5? So let's try with an example and let's know how we can find. So let's take the previous example only to know how can we optimize the previous approach. So before that, let's take a small graph example. So for example, let's say we have a graph, something which looks like this, which contains 3 and the adjacent cell would be 4 and the another adjacent cell would be 5. So now, so the other would be 5. So now let's somehow we have got to know the number of increasing paths from 3. For example, the number of increasing paths from 3 would be a single 3, another would be 3 comma 4, another would be 3 comma 5. So these are the 3 increasing paths from 3, right? So one would be single 3, one would be 3 to 4, one would be 3 to 5. So these are the 3 increasing paths. So now if at all we have got to know the number of increasing paths from 3, right, which is 3. So if at all, let's assume we have another edge which connects to 3. So let's say we have the 2 and 2 connects to 3. Now let's find the number of increasing paths from 2. So now we have got to know the number of increasing paths from 3, right? So which is 3. So if 2 is connected to 3, that actually means 2 will be in all the paths of the increasing paths of 3, right? I think it's confusing, right? So for example, let's find the number of increasing paths from 2. So one would be 2, one would be 2, 3, 4, one would be 2, 3, 5. If you see clearly, the number of increasing paths from 3 are the subsets of number of increasing paths from 2. You get it? So if this is the number of increasing paths from 3, so if we add 2 to the 3, that actually means 2 can be added to this, like this, right? So if 3 has 3 increasing paths, that actually means 2 is also having 3 increasing paths plus 1, which is a single 2, right? So I think now you got the formula. So if we know the number of increasing paths for any adjacent cell, for example, we have A node and we have B node, and B have some numerous number of edges which are connected to some other increasing paths. So if B have n increasing paths, So A will be having 1 plus n increasing paths. That will be the formula. So let's try with the matrix. Let's try how can we do with the matrix, and let's try how can we optimize by doing some DP or some cache approach. So let's check this example. Let's check the matrix and let's find the number of increasing paths using DP. So starting from this one, let's find out the adjacent cells which are greater than 1. So this one is not greater than 1. So coming back, so let's go to the other adjacent cell which would be 3. So now 3 is increasing, right? So let's go to 3. So now from 3, let's find the number of adjacent cells. Let's find the adjacent cells which are greater than 3. First one, which is 6. Of course, this is 6 is greater than 3. So let's go to 6. So now from 6, the adjacent cells are 1 and 2 and 5, right? So 1 is not greater than 6, 2 is not greater than 6, 5 is not greater than 6. So so that actually means there are no adjacent cells which are greater than 6. So there is only one increasing path. So now what we can do is, as we have come to some dead end where we cannot go anywhere, we can store the number of increasing paths from the dead end in this DP array. So now from this 6, the number of increasing paths would be just 1. So what I can do is I can store this 1 in this cell. That actually means 6 has 1 increasing paths. So now coming back to this 3. So now what I can do is, like I said before, A and B. If B has n increasing paths, that actually means A has 1 plus n increasing paths, right? So now if 6 has 1 increasing paths, now as of now 3 will be having 1 plus 1 increasing paths. That actually means 2 increasing paths, right? Which are, that is 1 3 and 1 is 3 6. So 2 increasing paths as of now. So now when we have come back to 3, now we have to go to 4, which will be the next increasing. So we have come to 4. So now from 4, let's find the adjacent cells which are greater than 4, which this would be 5. Now again from 5, let's find the number of adjacent cells which are greater than 5. So 1 would be 6. So now as we have already done with 6, what we can do is we can take the value from this DP array and just send that 1 to the 5, and just we have to do the formula, which is 1 plus n, which would be the number of increasing paths from 6 plus 1. So from 5, as of now the number of increasing paths would be 2. 1 would be 5, 1 would be 5 6. So now again coming back from 6, let's go to 8, because the another adjacent cells from 5 would be 8. Let's go to 8. Now from 8, let's find the adjacent cells which are greater than 8. So 2 is not greater than 8. So that actually means there is only one increasing path from 8. So we just add 1 here, and coming back to 5, we'll be sending this 1 to 5. So again applying the same formula, which actually means if 8 has 1 increasing path, that actually means 5 will be having 2 increasing paths. So what we'll be doing is we'll be adding an extra 1, right? So like for what I'm trying to say is, as we have added 1 already before, right? Single 5. So now we don't have to add that single 5 each and every time. So what we can do is just add the number of paths from 8. So this would be 3. So let's make it 3. So now again, so we are done with 5, right? So coming back to 4. So if 5 has 3 increasing paths, which would be one single 5, one is 5 6, one is 5 8. So if 5 has 3 increasing paths, that actually means 4 will also have the 3 increasing paths plus 1. So it would be 3 plus 1, which would be 4. So 1 would be 4, 1 would be 4 5, 1 would be 4 5 6, 1 would be 4 5 8. So that actually means 4 has 4 increasing paths. So coming back to 3, so now we have to add this the increasing paths from 3 as well, right? We have to update because we have gone to 4, and we have to send the number of increasing paths from 4 to 3. So we have already added a single 3 to this 2, right? In this 2 means it has 2 increasing paths, and one of the path would be a single 3. So now what we can do is you can just add the number of increasing paths from 4 to 3. So now as the number of increasing paths from 4 is 4, we can just add plus 4. So this would be 6, right? So coming back to 1 again, from 3 to 1. So as 3 has 6 increasing paths, right? So now 1 will be having 6 plus 1, which would be 7 increasing paths, because we haven't added the 1 previously. So now we have to add plus 1 as well. So we have done the path from 1. So coming back to this one, which would be this one, right? So let's find the adjacent cells which are greater than 1. So 1 would be 7. So 7 is greater than 1. We go to 7. So from 7 there are no adjacent cells, right? So 2 is not greater than, there are adjacent cells but not greater than 7. So 2 is not greater than 7. So that actually means from 7 there is only one increasing path. So we add 1 here. So we send this 1 to this one, and just say 7 has one increasing path. So that actually means one will be having two increasing paths, because if 7 has 1, that actually means 1 will be having 1 and 1 7. So this would be 2. So coming to this 6 is already done, because 6 is greater than 1, right? So we're coming to 6 is already done before. So 6 has one increasing path. So that actually means 1 will be having the number of increasing paths in 6. So we have to add 2 plus 1, which would be 3. I hope you're getting this, right? So now we are done with 1. So coming back to 7. So 7 is also done. Coming to 3 is also done. It's coming to 6 is also done. Now the thing is 2 is not done, right? So we have come to 2. So now let's find the adjacent cells from 2 which are greater than 2. So first thing, which is 7 is greater than 2, right? So 7 is also done, which, because it also has, we have found out the number of increasing paths from 7 is 1. So let's send that 1 to the 2. So if 7 has one increasing path, 2 will be having 1 2 1 2 7. So 2 increasing paths, right? So we add 2. So we come back from 7 and we go to 6. So 6 is also done. 6 has one increasing path. So that actually means 2 has, from 2 we have 1 2 and 1 2 6. So as we have already added this single 2 in the previous path, so all we have to do is just add the number of paths from 6. So now it would be 3. So 2 will be replaced by 3. So now we come back from 6 and we go to 8, because 8 is greater than 2. So now we have, as we have done with 8 before, so we will be just sending the number of increasing paths from 8, which would be 1. So if 8 has one increasing path, 2 will be having 2 will also have one increasing path. So what we have to do is just add this 1 to the 2. So this would become, oops, so this would become 4. So yeah, so we are done with 2. Now going to 4. So we are also done with 4. Now going to 5. We are done with 5. Going to 8. We are done with 8. So that actually means we have done with the entire matrix. So but we didn't still find the number of increasing paths in the entire matrix, right? We just found the number of increasing paths from this cell, from this cell, from this cell, from each and every cell, but we didn't find the number of increasing paths for entire cell. So how do we get the number of increasing paths? So we can get that just by adding all the increasing paths. That's it. 7 plus 3 plus 1 plus 6 plus 1 plus 4 plus another 4 plus 3 plus 1. So let's add this. So 7 plus 3 would be 10. So this would be 11, right? So this would be 10. This would be another 11. So this would be 8. So entirely this would be 30. So that actually means the total number of the number of increasing paths in this matrix will be 30. So like this is how you find the number of increasing paths by using dynamic programming approach. So now let's try implementing this solution. So here we are having a method called as count paths, which passes parameters which contains a matrix. So what it expects is it requires the number of increasing paths in this grid. So first things first, what I'll be doing is I'll be creating two variables just for the number of rows and number of columns, which will be m and n. So I'll be assigning that to the m and n matrix dot length, and n would be matrix of 0 dot length. So now, as in the previous approach using dynamic programming, we have used an extra grid, right? So for that, what I'll be doing is I'll be using an extra grid here as well in the implementation. So this would be dp, and dp would also be of size m into n. So now, how do we do before? We have started from the first element in the matrix, right? So for example, let's take this is a matrix. So now we have started from the first element itself. So I'll be using the normal two nested for loops for int I is equal to 0, I is less than m, I plus plus, and for int j is equal to 0, j is less than n, j plus plus. So if dp of I comma j is equal to 0, then I can do dfs from here, right? So why am I checking if dp of I comma j is 0? If dp of I comma j is 0, that actually means we haven't visited that cell anytime till now. So if at all it is not 1, not 0, that actually means we haven't we have visited already. Because for example, let's say we have visited 4 here already before. Let's assume that. So if this would be initially 0, dp of this cell, which would be 1 comma 1, would be 0. So as each and every number is an increasing path, so definitely if we have visited that cell, we have at least put 1 there. If it is not even 1, if it is 0, that actually means we haven't visited there. So if it is 0, then I'll be doing dfs. So what are we doing in dfs? So what I'll be doing is, in dfs I'll be passing the row and the column, which would be x and y, and the matrix. So first thing is, first I'll be checking if dp of x comma y is 0 or not. So okay, let's skip that for now. First thing is, I'll be using a variable called as number of increasing paths. So this would be initially 1. So why am I taking it 1? Because a single element is also an increasing path, right? So for that I'm initially fixing that the number of increasing path for this cell would be 1. So now I'm using a for loop to go to 4 directions. So I is equal to 0, I is less than 4, I plus plus, and for this purpose I'll be using two arrays. So let's say one array would be dx for rows 0 0 1 minus 1, and dy for columns 1 minus 1 0 0. So this combinedly would become one direction. So 0 and 1 would be going to right, and 0 and minus 1 would be going to left. 1 comma 0, which would be down, the minus 1 comma 0 would be top. So what I'll be doing is, I'll be finding the adjacent cell by adding to the current cell. So int new cell, which would be, let's say it's u, this would be x plus dx of I, v would be y plus dy of I. So these are the adjacent cells. First things first, I have to check whether those cells are valid or not. So for that I'll be using a method called as valid. I'll be passing this u and v, and if it is valid, what we have to make sure is that cell value should be greater than the current cell value, right? That's the main thing. The matrix of u comma v should be greater than matrix of x comma y. If this satisfies, I can perform dfs by passing this u comma v and the matrix. So now somehow this entire dfs is done for the adjacent cells, and what it does is, it will be sending the number of increasing paths from that adjacent cell, right? For example, let's say we have found out the number of increasing paths from 4. So now we are at 3, right? So this 4 will be sending the number of increasing paths to 3. Now, as we have done before, we have to do some calculations here. So let's say we have something called as a result. This result contains the number of increasing paths from the adjacent cell. So now, as I said before, what we have to do is just add the number of increasing paths from adjacent cell to the current cell. So that actually means the number of increasing paths plus is equal to the result, right? Because we have done the formula before, the number of increasing paths from adjacent cell plus the current cell. So in the question they have given some extra case here, which is, as the answer may be very large, we have to return the modulo of 10 power 9 plus 7. The reason why they are trying to say this is, as the input might be very large, so there might be a case where the answer would exceed the integer limit. So for that case, what they're trying to say is, return the answer by doing the modulo of 10 power 9 plus 7. So for that I am trying to do that here. So number of increasing paths percentile is equal to, let's say this is a mod. So for this I'll be using a constant variable at the top. So let's say final int mod, it should be 10 power 9 plus 7. So this is gonna be 1. So 9 zeros, 3 4 5 6 7 8, ninth one would be 7, right? So I'll be just doing the mod for that. And later what I'll be doing is, as before, when we have found out the number of increasing parts from particular cell, we have to, after at the end, we have just added the sum and return we have got to know the answer, right? So what I'll be doing is, instead of completing the entire DFS here and finding the sum in the DP array, I'll be doing the sum here itself. So for that, what I'll be doing is, I'll be taking a variable called as let's say long answer. So I'll be adding the sum to this answer itself here only. So answer plus equal to would be number of increasing parts. So again, same here, we have to do the modulo because answer might exceed. This would be mod. So now, as we have done with this current cell, we have to store the number of increasing parts from this current cell to the DP array. So DP of x comma y would be int of, because this is long, right, we have to do some typecasting. So it should be number of increasing parts, and we have to just return the number of increasing parts from current cell to the previous cell, DP of x comma y. So this is the implementation of DFS. So we have forgot the main thing, which is implementation of valid function. So let's implement that as well quickly. So this would be a boolean which is named after valid, which contains two parameters, row and column. So the main case is, the row should be, so row should be greater than or equal to 0, and column should be greater than or equal to 0. Row should be less than m, and j should be, which is column, should be less than n. So if the cell which we have found out is inside the grid, then only we can say that grid is that cell is valid. So if it is valid, then we can check that cell contains a number greater than the current cell or not. So yeah, this is, yeah, we have forgot, we have to return at the end, we have to return the answer. So return int of answer. So as the answer is a long type, we have to typecast to int. So yeah, this is pretty much the solution, this is pretty much the implementation. So let's try to run this code, and let's see we don't have any compilation errors. Oh, we got the wrong answer. Where did it go wrong? Oh yeah, so we have forgot a main case. So when we have got, when we are going to an adjacent cell, we have to know whether we have already visited that node or not, right? So for that, I mean, whether we have visited that cell or not. So for that, we have to check at the beginning here. So dp of x comma y is not equal to 0, then just return dp of x comma y. So as we have seen the previous case, which is we have gone from 3 to 6 and 5 to 6, so 6 is already visited, right? So we don't have to do the same repetition process again. This is the main case, this is the main thing which works for dp. So let's see if there are no any mistakes here. So yeah, I think this works. Let's see. Yeah, it got accepted. Let's try with some extra test cases. Yeah, so let's submit the code. Yeah, so it got succeeded. So this is how you find the number of increasing paths in a grid. So as I said before, the prerequisite question for this would be the longest increasing path in a grid. So I would recommend you to solve that question before this, so that you can get a clear idea. If you have solved that question, then you can definitely solve this question for sure. So if you like the video, please make sure you like and subscribe. Thank you.